Yes, sir.
Yes, sir.
Okay, very
Yes,
good.
sir.
Okay. Now, yesterday I have tried to introduce the basic concepts of machine learning, uh, and there we have discussed some problems about predictions, right? First one is the classification, and second one I talked about that estimation, or where we use regression to estimate, and we discussed the differences between them. And I have tried to introduce the very basic model of machine learning, a classification model called perceptron. Okay, that is a linear model, and we have learned the algorithm how to
Devendra, please press Control L for full screen.
okay, okay. Control A, right?
Control L.
L, okay. Okay, is it clear now?
Yes, yes.
Okay, so PLA we have discussed yesterday, and then in very fast mode, actually, I tried to explain that whether machine learning is feasible or not. And finally, there where I discussed the generalization mainly, and there I tried to introduce the VC dimension. But unfortunately, this is a very short session, so it was very difficult for me to consolidate everything, which normally I take 5 to 6 hours to introduce VC dimension. I had to do that in maybe in 15 minutes. So I'm sorry about that. Maybe later, if opportunity comes, I'll be very happy to explain what the actually VC dimension is, and what its importance in machine learning. However, today we will be going to the estimation part of it, that is regression. There is linear regression, obviously that is the simplest one, and another one is very famous, that is the logistic regression. Though it is a regression, but it is actually a classification. In many cases, we do not like to classify the objects in black and white mode. Rather, we want to give with some probabilities. I'll come to that point when we start logistic regression in detail, but we'll start in the beginning about the regression. However, today's lecture will contain the simple linear regression. Then obviously I'll extend that to nonlinear regression, how to use nonlinear function in estimating something, and finally the logistic regression. You see that this one is just in a very high level presentation. I guess that if I present using my handwritten notes, which I shared with you, I'll be more comfortable, and I think it would be easy for you to understand as well. So I'll go there, and then uh, I'll just explain. Okay, just 1 second. I do not know. Just 1 second. How to present where that particular stop presenting, then I'll come to this one window, and then the linear regression. Okay, this is my handwriting one. I guess you will be able to read it. Can you see this?
Yes, yes.
Yes, sir.
Okay, so I'll just explain a simple problem, and then I'll try to explain the mathematical aspect of regression. And I guess all of you have already studied this particular formula mainly in your class 12, 11 or 12, as well as some in engineering, or whatever you have done in your bachelor courses. Just I'll recapitulate that very fast, the mathematics of it, and you will see that it is a good fun. Okay, let me sorry, let me explain a problem first, and then I'll go for it. You see, the linear regression, in regression or in estimation, normally what we do, suppose we have a data set, right? And maybe we have to predict the rainfall in a particular place. Okay, and to predict the rainfall in a particular place, there maybe says we have to collect the data for past few years. Okay, and say rainfall depends on several parameters. It is always, we have to know that, right? That whatever the outcome or output is, that is y, rainfall y, that will depend on maybe temperature, atmospheric pressure, humidity, several other features, right? But let me explain that let us assume the rainfall depends only on one parameter, and then I will extend it for the several parameters. Okay, let us assume the rainfall depends only on temperature. Okay, and we have collected the data for say capital N number of instances. Say on a particular day there was temperature was x1 and rainfall occurred was y1. x2 was the temperature, rainfall was y2, xn, small n, and yn was the rainfall, x capital N was the temperature, and y capital N was the rainfall. So this is the data set we have collected. This is the dependent variable, right? And this is the independent variable, and rainfall is the dependent variable, and rainfall depends on this temperature. So y is a function of temperature. As yesterday I said that the outcome, right, y, this outcome, our objective is to express this outcome y as a function of x, the target function, and we have to find that mapping or the function from this data set. Okay, maybe it's thousands of instances we have got, and from that data set we will try to find out what the function is, right? Once we get the function, now on a particular day maybe the temperature is x star, and what should be the outcome y star. So we have to find out that function. That is the hypothesis, right? Yesterday you were trying to find or talk about that our objective is to find a hypothesis that would be identical to our unknown target function. Now say f is the target function, okay? And now let us assume that y is a function of x, fx, and this function, we are assuming the function is a linear function of x, okay? Where it is linear function, we know there are two parameters a and b. It is ax plus b. In general, yesterday we have represented as b as w0 and a as w1, right? w0 plus w1x that you can consider, or maybe ax plus b. This is how we are familiar with as a linear function. Now you may argue, who said that this is linear? Yes, it may not be linear. It may be a quadratic, ax square plus bx plus c, or it may be a cubic function, or maybe it is a sinusoidal, or maybe a exponential, or combination of that, or several other. But let us assume first it is linear, then I will go for the non-linear regression. There I will try to explain. Moreover, we will consider that the function, that the rainfall will depend on several other parameters, and it would be a function of several variables. Okay, I will explain that. Don't worry about that. Try to understand this clearly, and then it would be easy for you guys also to extend it. Mathematics we will try to understand here. Now say on a particular day, this is the function, right? We are assuming. In beginning, we do not know what this AB are. We'll try to find out this AB from this data set. Okay, but assume that ax plus b is the function that would help us to map the temperature to the rainfall. Say on an instant, on a day, nth day, your temperature was xn and your actual rainfall was yn. This is the actual value. But if I yin this function to predict what the rainfall would be when the temperature is xn, we know, right? I denoted that as capital Yn, so it would be axn plus b. Axn plus b. So this is the estimated value. We do not know what the AB are. We'll try to find out from this. So this is the actual value, Yn, and your estimated value is axn plus b. That is the estimated value. Now you see, when you get something, estimated value, you will intend to find out how much error we are considering here. So error would be Yn, that is the actual value, minus estimated capital Yn. I gave here square. You can always consider this as an absolute value of Yn minus capital Yn. Absolute value is also okay. But absolute value if you take, there will be some difficulty in handling. People always have different reason to consider the square error, right? This is the square error we are considering. But you can, for me actually, if we consider the absolute value, that is also okay. But there are some difficulties you will encounter handling this absolute value. Absolute function is not well behaved function, right? We know that. So it is better to avoid that. That's why we consider it as a square error, and this is okay. And this is almost, this is actually similar to the square error, sorry, absolute error. So En, the error due to the nth instance, actual value is Yn and estimated value is capital Yn, right? So we are taking this square. Now what would be the total error? Total error for x1, it would be y1 minus capital Yn, y1 whole square, y2 minus capital Y2 whole square. So you sum up all the errors, right? Errors for all the points, and you will get the total error. And then you divide by capital N, you will get the average error, right? This is the one which gives us the total, or rather the average square error. Remember that. Total error is sum of square error, we say SSE, and this is the average error. We have got it. Now you replace this Yn as Axn plus Xn plus B. This is very simple. Yn minus Axn minus B whole square. So this is our average error, right, for all the data points. So this is where to calculate the error, we use this data set. Now clearly, if you just analyze this particular expression, this error, right? This error contains capital N, that is nothing but a number of data points you got. This is a summation, don't worry. All these Yns are known to us. All the Xns are known to us. What we do not know are A and B, two parameters we have used in constructing this linear function. Okay, so this is the error. So I can always express or represent this as a function psi AB. This is a function of A and B, two parameters. Okay. Now you see what our problem was. Our problem was to find a mapping, right? A function that would help us to map this temperature to the rainfall. Now, if we assume that function is Ax plus B, and we got this error. Now, what our objective would be to minimize this error. When this error is minimum, obviously that function will give us a best fit mapping between temperature and rainfall. That is very clear, right? So now our objective would be to find AB, this A and B, two parameters that minimizes the error E, right? So that's what our job is. I hope this is clear. We had this problem. We could come up with an error, an objective, right? And we want to minimize this. To minimize this, we can change our A and B only, right? Other values X and Yn, obviously that is given. We cannot do anything. Now come to the next slide. And yes, so here what we have E and B, right? I would have written E here, but you know that is there. So here, what we do, how to reduce that? This is very simple, right? That means Newton has given us the process, and all of us are familiar with this maxima minima. To minimize, what we have to do, we have to differentiate the function with respect to the parameter. And since this is E is a function of two parameters, we are doing partial differentiation. Very simple. Del E del A equal to 0, del E del B equal to 0. Let us go back to the earlier one and see the function here. If I differentiate this with respect to A, let me do it here and then I'll come back there. 1 by n is a constant, summation is also will be there. Now if I differentiate this whole thing with respect to A, right, we have to follow the chain rule. So it would be 2 into the whole thing, and if I differentiate the internal this one with respect to A, it would be minus xn. So it would be this 1 by n summation 2 into Yn minus Axn minus B into minus xn. Let's see. Okay, that is 1 by n, 2 into in minus axn minus b into minus xn equal to 0. Now I have written it in a better form, that is 1 by n summation. You can get rid of these 2 and this minus as well, they are constant. In fact, you can get rid of this n also, but this n is required. That's why later I have to bring it back. So I kept it here. So it is xn into in, right? Xn into in minus axn square minus bxn equal to 0. Very simple. Huh? This is a simple calculus, which you have, all of us are familiar with, right? And this is just like in our mind. It's like a plus b, a 2 plus 2 form, right? So now you just break it down. You keep this minus part this side. What I can write, this will become plus. So a constant into 1 by n summation xn square plus b into 1 by n summation xn, and this part I have taken, right, the other side. So it is 1 by n summation xn yn. Very simple. A, b unknown we have kept in the left side, the other part we have taken in the right side. Now 1 by n summation xn square, what is this? This is nothing but the average of x1 square, x2 square, x3 square. Average of the square, right? X square bar. We represent that in statistics as x square bar. We know that this is nothing but x1 square plus x2 square up to xn square divided by capital N. And we know, right? Summation xn by n, right? That is x bar. We are familiar with this statistical term. And this is the dot product of x and y, right? x1 y1 plus x2 y2 plus xn yn by capital N. So this we can write that xy bar. Now you can always consider these as an equation, right? We can calculate x square bar, we can calculate x bar, we can calculate xy bar, and this is an equation. Then come to this one, del E del B equal to 0, right? Now del E del B, if you do, if you remember the expression, this 1 by n will be there, summation will be there will be 2 into this expression, and with respect to b, if I differentiate, it will be, there will be a minus 1. So you get rid of this minus 1 and 2, it will be very simple. I have written in one step. You just take this a into 1 by n summation xn, that is a x bar, and b, right? There is nothing, summation 1 and 1 by n, so it is b equal to y bar. You just do yourself of your own. I want you to practice it once. It is very easy. So this is the equation we got. Now it is very simple, right? Now we have gone back to maybe class 8. We got an equation here, right? And this is another equation. Simultaneous equations, right? 2 equations, 2 unknown. And it is very easy to solve. How to solve it? You multiply this equation by x bar and subtract from here. Okay, that's what we have done. So if I do that, a is there, so x square bar minus, you multiply this with x bar, it would be x square bar minus x bar square, which, and this b will be cancelled out, and this side it will be xy bar minus x bar y bar. You multiply this equation by x bar and subtract from this equation, and this is very simple expression, and we got an expression of a, right? This is very simple. Okay, now once we get a, our objective is to express y in terms of x. Now if I get a, just what is the actual equation? Actual equation is y equal to ax plus b, or rather ax plus b equal to y, right? Now you subtract this equation from the original one to get rid of this b, right? Actual equation is ax plus b equal to y, right? That is 1. So you subtract from that, what you get is y minus y bar equal to a into x minus x bar, correct? And we know what this a is, so we got rid of b. Actually, you can always find out what the expression for b, right? You can replace this a in this equation, you will get one complex equation. But anyway, we do not need to bother about b, so we got this equation from where we can write y equal to y bar plus a into x minus x bar. This equation, right? Here all are known, right? Now you put the value of x here, you will get the value of y. So if your x value, the temperature is x star, your y star, right? Predicted rainfall will be y bar plus a into x minus x bar. What is a? A is this expression, and given the x1, x1, x2, x1, x2, x3, xn, and y1, y2, y3, yn, we can always calculate this one. By the way, you may be worried about remembering this one, right? Now let me tell you what actually it is. Now, if you remember the variance of x, okay, actually I have written here wrong. Actually, variance of x, what is variance of x? That is summation xi minus x bar whole square, right? And obviously there will be 1 by n. Now, if I just split that one, right, if you break it up, it will become x square bar minus x bar square. This one is nothing but the variance. And variance is represented as the standard deviation square, which is nothing but sigma x square. This is the one. And what about this? Can anyone say that? I'll wait for your response. What is xy bar minus x bar y bar? I am wrong here. This is not variance. Variance x is this one, the denominator. Can anyone say what is this one? Xy bar minus x bar y bar? Please. Who will say? If this is the variance, this one is nothing but covariance of xy. This will be covariance of xy. So it is covariance of xy by variance of x. That is A. It is easy to remember, right? So it would be, now what I can write here, covariance of x by 1 sigma x I have written. I introduced 1 sigma y here, but this sigma y I have to cancel out, right? So it is sigma y and another sigma x I have written here. So this whole expression, this will be covariance of xy. So it will be covariance of xy by sigma x sigma y into sigma y by sigma x. Now what is this? Covariance of xy by sigma x sigma y, that is nothing but the, what is this? Correlation coefficient. Correlation coefficient into sigma y by sigma x. So this is A. Remember that one. So if you have, just 1 second. Okay, I came back here. So we got a set of data, and what we have assumed that y value, that is rainfall, depends only on temperature, only one parameter, and then we could able to find out a linear function, because what we have assumed that rainfall depends on temperature linearly, right? So it is a linear dependence. That's why you have assumed as y equal to ax plus b, and we could able to find out what the value of ab is. And obviously there will be some error, that the square error we have defined, and we have minimized the square error, right? Now I'll just go to the nonlinear representation, where it is not necessarily that the function will be depending on the linear regression. Okay, it is not necessarily that linear regression depends on your or linearly. It may be say non-linear as well. I'll come to the non-linear, but before that, let me explain what happens if, say, rainfall depends not only on temperature, but it depends on temperature, pressure, humidity, several other parameters. Now that is the general one, that not necessarily that a particular output rainfall depends only on one parameter, but multiple parameters. So let me generalize that and we'll explain it. What we have, let us go back to our normal representation. Suppose we have a data set here, xn, that is a vector, right, which is actually d-dimension, but we have introduced the dummy variable. Yesterday we have done the same thing we have got, right? Dummy variable xn0, that is 1. So xn is a d plus one dimensional vector. So what I can say is that xn is a rd plus one. Okay, since we have grown up, that's why maybe I'll just introduce this one for a in a vector form. Okay, so xn belongs to rd plus one, that is d plus one dimensional real space. Okay, maybe the xn0, that is the dummy variable 1, xn1 you can assume as a temperature, xn2 maybe as a pressure, and xn3 maybe as a humidity. So there are say 4 if you have. So there are several other parameters may be there. Now suppose you are say trying to estimate what may be the credit limit of a customer. So in that case, your data will be much more higher dimensional. So xn0 will be there, right? That is the bias or the dummy variable. Then maybe xn1 is your age, xn2 will be the annual salary, and several other parameters you can add that. So this will be a vector. And yn is the actual credit limit, right, for the past customers. And here it is rainfall. And how many data set we have got? Capital. So this is our training set. We are familiar with that. And what is this yn here in our this case? In the perceptron case, it was either +1 -1, but here it is the actual rainfall. That is a real value, belongs to R. It is not this, but it is real value. Okay. So in the linear regression, single variable dependency.
Can you repeat that part? Like why you are adding that x0, that dummy variable, for the use of that bias?
Okay. Yeah, actually yesterday I tried to explain. Once again, I'll just repeat that one. When we explain this perceptron, this is the picture. Okay. Now we had two sets of data set. This is plus, another one is minus, right? Two class. Now our objective is to find out a line, something like this, that would separate these two classes, right? That is the boundary. That's what our objective is. Now, whenever you are trying to find out the boundary, if you have say in two dimensions, right? This is the x1 axis and this is the x2 axis. Now, what is the equation of this line? It is w1x1 plus w2x2 plus w0 equal to 1 or equal to 0. It's like ax plus by plus c equal to 0, right? Ax plus by plus c equal to 0. Now, so we have got a, b, c, three parameters. Now here it is in two dimension, right? So if you had only xn1 plus xn1 and xn2, what we are doing? We are multiplying this xn1 with w1, xn2 with w2. How about the constant term? Right? That one I am denoting as w0, that's c, and just to put in the summation wi xi form, we have introduced dummy variable xn0, which is 1, so that we can write this particular line as w0x0 plus w2x2, w1x1 plus w2x2. Okay, so x0, it is not necessarily that you can introduce x0. You can keep it separate. Actually, in some cases, SVM will keep it separate. But in this case, just to represent this line in easier form, W transpose X, we are introducing the 0th part. xn0 for the value is 1. That is for the mathematical representation. You understand? So W0x0 plus W1x1 plus W2x2. You understand?
So, sir,
Yes.
can we say this xn0 is, you are equating it to the C of the equation?
That's right.
Okay.
We have
Okay,
to,
right,
and
sir.
that is the actual issue. But
Oh,
at the
okay.
same time, we could keep W0, right?
Okay.
We do not need
Okay,
to add x0, but x0 we have added just to write that in the good form, right? In the vector.
Okay. Thank you, sir.
Yeah. Okay, and that is very important. If we do not do that, if we just make that c equal to 0, what she said, then this line will be always passing through the origin, right? It will not be moving.
Oh.
So you understand that, right? So that's why c is very important, and we have to keep the w0 and just to put in the vector form in easy form. That's why, and that would help us to write our program as well. So we have introduced this xn0, that is the dummy variable, and that is corresponding to the bias, right? Bias is a very famous term in machine learning. We'll be using everywhere. Okay, Sarup, is it okay?
Yeah, it's okay. And one more thing, like some way, I mean, that is 0 is fine, it will pass to the origin, so we needed, let us assume 1. But if we range in some other values, how it will be back? Let us assume it may be other than 0, it may be any value, if we consider. Then is there any impact that is going to happen in placing that boundary? Instead of...
I could not able to understand actually. Somehow it is getting distorted.
Because x naught we are taking 1.
Yes.
X naught we are taking 1. So can we take any other value? Can we take any other value other than 1?
Yes, you can. See, you cannot take any value, but it has to be a constant, right? It has to be a constant. You can take it. If you take 2, then W0, suppose your constant value is say 5, right? If you consider x0 equal to 1, the constant value will be 5. If you take say x0 equal to 2, your constant value will become 5 by 2.
Right. No, I am talking about like since during the learning, the value of B will not going to change. So it will not, only the weights will going to change. Now, that value, the decision to take that value of that bias, whether it will going to give an impact in quick convergence.
No, it will change. We are changing W0, right, in every iteration while learning. W0 is a parameter which we are learning.
If you take it as a weight, then definitely it will change, right?
It is weight, right? We are taking that as a weight. In PLA also we are modifying W, right? W0.
Right.
Yes, we are changing it. Here also you will see that, right? Here also, when we discuss about this regression, we will be finding out the optimum W0 as well. W0 obviously is an unknown, and we will be able to find that out in our learning algorithm. We have to find it out. Okay, in neural network as well, you know, right? So W0 is an unknown, like other weights as well. W0 will be another weight, and that works as bias. Yes. Okay, Swarup?
Fine.
Okay. Now, here, let me generalize it for several variables. Okay. Now, suppose rainfall depends on temperature, pressure, humidity, and several other parameters. And those parameters are x1, x2, xd. So, y is equal to f of this function of x1, x2, or xd. So far, we have considered only one variable. Now, I am generalizing for multiple variables. Don't worry, I'll just try to explain it, and I am assuming that you have got some basic vector, you're familiar with vector notations and some vector operations, basic vector operations. You have any doubt, please tell me. So this is what the function is, and let us assume f, this function is linear function, because we are discussing only linear regression. I will explain that for nonlinear regression after this one. Now, what is linear function of d variables? There will be W0, x0, right? Dummy variable, I have added 1 just to write its summation. W1 x1 plus W2 xd. And what this is? This x0 is equal to 1, dummy variable we have got. So this one I can write as a summation Wi xi, I equal to 0 to d. And that is nothing but this vector form W transpose x. What is W? W is a vector, right? Weight vector. You see Swarup here, W0 is included here. So this is a d plus one dimensional vector, W0, W1 up to WD. If you take the transformation, it will become a row, then x, right? X is nothing but x0, x1 up to xd. X0 value is 1. So this is also d-dimensional vector. This will be a column. So wx, W0 x0 plus W1 x1 plus WD xd, right? So this is 1. This is W transpose x. So this is the function, right? We are assuming is a linear function. Now, for the nth data point, like earlier case, this is the data set whatever we had. In the nth data point, your vector was xn, right? Xn was the vector, and your actual value was yn. But if we assume this as your estimating function, predicting function, then what should be the value, estimated value? Estimated value will be W transpose Xn. Like earlier case, whatever we have done, Axn plus B. So this is our estimated value. Yn is the actual value. And we can always calculate the error like this, right? For W transpose Xn, this is the estimated value minus actual value, that is whole square. Note that in the previous case, I have written Yn minus W transpose Xn, right? The other way around. But since it is a square function, does not make any difference, right? So I can always write this one. Now, what will be the average error for all the capital N number of data points? So you sum this up over n equal to 1 to capital N and take the average, right? This is the one. Don't worry about all these notations. Once I explain, it will be very easy. Okay, so what we have here, W transpose X1 minus Y1 whole square plus W transpose X2 minus Y2 whole square up to W transpose X capital N minus Y capital N whole square, right? That one we have. Now, what I'm claiming, this can be written as in a vector form, so simple this one. What is this? I'll talk about. 1 by n is there, and the summation of this can be written as norm of, this is the norm, right? All of us know our magnitude of a vector. What that vector is? Xw minus y. What is x and y, I'll explain. So this whole expression, right? This is a huge, if capital N is a 1000, it would be a sum of 1000 terms, right? So that can be written as a norm of a 1000 dimensional vector, that is xw minus y. What is this capital X? Okay. Now, before I explain that one, let me tell you what this norm is. Okay, that is nothing but the norm is magnitude of a vector A. Suppose you have a vector A, and vector A is like this, A1, A2, AD. Now you tell me, what is the magnitude of this vector? All of us know, right? A1 square plus A2 square up to AD square. You just square the components and sum them up and take the square. Okay, remember that. We have done that in class maybe 11, 12 now. We used to study in graduation level vector A. If you have, say, a vector A, A1I plus A2J plus A3K, magnitude will be A1 root over A1 square plus A2 square plus A3 square. All of us know that. So if you have d-dimensional vector, it would be this one. That is the norm. And you take the square, it would be the square term. Now, in bit here, I have written one bit expanded term, right? Vector, that is xw minus y. What is capital X? Capital X is a matrix we have constructed like this. You have got x1 as a vector, right? x1 vector, that is x10, x11, x12, x1d. This is a column vector x1, and we have written the transpose of x1. So you write the first data point, you write the second data point, you write the nth data point. So you will get a matrix of the form capital N cross D plus 1, right? So we have written all the data points in a matrix form. First data point, second data point, third data point, nth data point. So how many rows will be there? N data, capital N number of data we have. So this is a vector of this is a matrix of dimension capital N cross how many dimension the data is d dimension plus the dummy variable. So it is d plus 1. N cross d plus 1. What is W? We know that same W0, W1, WD. And what is capital Y? You have got this actual value, right? Y1, Y2 for this data, value is Y1. This data actual value is Y2. For this data actual value is capital Y capital N. So it is a vector of dimension capital N. Okay, Y1, Y2, Yn. So you just construct this matrix, data, values, construct this capital Y. Now, if I just construct this XW, what is XW? You multiply this and this, right? XW. You see, this into this. That is W0, X10, W0, X11, W1, X12, W2, X1D, WD, right? So this into this. That minus Y1. minus y1. Then this one into this minus y2. This one into this minus yn. So it would be a, this xw minus y will be a n, capital N cross 1 vector, right? Because if I multiply n cross d plus 1, and what is the dimension of this one? This is d plus 1 cross 1, right? So it would be n cross 1. And this is also n cross 1. We can always subtract and we can always calculate this one. And that is a n dimensional vector. You find out the norm of that, right? What you have to do, you just take the square of each term. You sum all the terms and then square root. So this whole expression error can be written as in this vector form. Okay, I guess I could able to explain that. But unfortunately, if I am not able to, please, you just see this one, you write down the steps, you will get it one. If you know the definition of norm, if you know how to multiply that, and it is very easy to see the dimensions of these matrices, and you can write down this one. Okay, in the matrix form or vector form, you can always write average error is equal to 1 by n into this. Okay, and in this, x is known to us, y is known to us, only unknown is y. So this is the error function. Actually, why am I doing this is that it would be easy for us to write the program, and ultimately our objective is to implement that in machine. Machine will do that. Don't worry, it is very easy. Okay, so we got this average error. Now our objective would be to find this w that contains w0 to wd, d plus 1 unknown parameters we have to find out that would minimize this average error. Now come to the next one. It's easy. I have written here xw minus y as this one. Okay, and what is this xw minus y whole square as this one, right? Yes, in the previously I was trying to explain that. So e equal to this expression. Actually, it is easy to demonstrate as well. I'm doing some vector differentiation, or we call it is the grad, right? This is the representation grad with respect to w we take. Don't worry, you just consider this as a whole square and you differentiate this with respect to w. So 1 by n is there, so 2 by n, this 2 will go, and this whole thing, right? xw minus y, this one forward. So we differentiate this with respect to w, but we cannot write differentiation here because this is a vector. So we had to write here grad. We all know, right? In vector, we do gradient. So that is means del w0, del w1, del wd. Don't worry, this is the one. But here in the vector differentiation, you can consider this as a whole square and just simply differentiate this with respect to w, considering that it is a square function. So 1 by n is there, differentiate this, the 2 will go, and this expression, right? And then you differentiate the whole thing with respect to w, you will get an x. You see, I didn't write x in the right side. Instead, I wrote here x transpose here. Does not matter, right? Either left, right, you can write it. If I just write here x, the matrix multiplication is not possible there. This is a n cross 1, and this is again n cross d plus 1. If I write here, so you cannot multiply. Instead, I have to take the transpose of x and write in the left side. You see, x is n cross d plus 1. You take the transpose, it will become d plus 1 cross n. And this is n cross 1. So you can multiply, and the ultimate resultant matrix will be d plus 1 cross 1. Okay, so simple. That's why I had to write here x transpose. Now this is equal to 0 from Newton's rule. We know maximization. Then simple, 2 by n, you can get rid of this 2 by n, multiply this. What is that? X transpose xw, right here. And here x transpose y, you take in the right hand side. So it's very simple, right? Actually, this is what we have done when I have shown you, demonstrated you for single variable linear regression. So this is the equation. What is this? This is nothing but d plus 1 linear simultaneous equations of d plus 1 variables, w0 to wt. Okay? You see that x transpose x is d plus 1 cross d plus 1. W is d plus 1 cross 1. And x transpose y, x transpose is d plus 1 cross n, y is n cross 1. So it is again d plus 1 cross 1. So both side dimension are matching. This is nothing but d plus 1 simultaneous equations written in one simple form, right? That is the advantage of matrix form or vector form, you can say. So this is d plus 1 equations, linear equations of d plus 1 variables. Forget about this part, but we can solve, right? We know several analytical method to solve it. The Gauss elimination, or what is that? There are several other, I just forget the names. So Gauss elimination is one, and anyway, I cannot remember. It is not coming in my mind. So there are several method in numerical mathematics, and we have obviously written our programs when we studied, say, C or basic algorithms we learned. So we have we know that how to solve linear simultaneous equations, right? So this is a set of linear simultaneous equations. We can solve this for W's. Another way, if we just go for matrix further, you see this W can be, you can multiply with X transpose X inverse both sides in the left side, and you will get this one. Okay, and you see this whole expression I have written an X dagger Y, and this is nothing. X dagger is X transpose X inverse X transpose, and this is called the pseudo inverse. You see that X transpose X is a n cross d plus 1, and X transpose X will be a d plus 1 cross d plus 1, right? This is a square matrix. It's a huge matrix. X is a huge matrix. Suppose you have got a data in 2 dimensions. With the dummy variable, it is 3 dimension, right? So, and you have got, say, 1000 data point. X is 1000 cross 3, but X transpose is 3 cross 1000. So, and this is 1000 cross 3. So ultimately, X transpose X will be a 3 cross 3 square matrix. This is not a huge matrix. Now, if your data you are having, say, in 10 dimension with 10 parameters, so it would become 11 cross 11 matrix. And very likely, right, we have to find out the inverse. Does all matrix exist inverse? You can exist inverse, or can you find out inverse of all matrices? No. Right? If the matrix is singular, that means if the determinant of the matrix is 0, you cannot do that. But very likely, if you have, say, huge amount of data, X transpose X is non-singular and inverse will exist. If it does not exist, obviously the equations will be dependent, right? You cannot solve. But anyway, we have got several other methods, numerical methods, the Cramer-Rao theorem, right? Rao in ISI is old director. And anyway, Rao has given one formula how or technique how to find out the inverse of singular matrix or approximation or something like that. Okay, anyway, but very likely that X transpose X will be non-singular. You can find out the inverse. You can find out the inverse and then multiply with xt. You will get X dagger. Once you get X dagger, you multiply with this Y, you will get W. This is the one. So you get the W. Once you get the W, you get an unknown X star, right, which is a vector, and then you can always find out what would be the value of Y star, that is W transpose X star. Okay. So what we got here is, let's stop this sharing. Okay, so first we tried to discuss linear regression with single variable, and then I have tried to explain that how to extend that for multiple variables. Does not matter, right? Now the same formula, whatever I have discussed now here, what will work for single variable, 2 variables, 3 variables, 4 variables, 100 variables, right? And all these programs in tool, it is available, and you can use those tools to solve for this W. What you have to do, you construct capital X, write down the data points, does not matter how many data you have, then you write down the capital Y, you calculate X transpose X, find out the inverse, multiply that with X transpose, and then capital Y, right? You will get W. Very easy. Now, what is nonlinear? I'll present again. I'll go back there. I close that one. Just 1 second, let me open. Oh, now I'll go back to my actual presentation. I'll go back to this. I'll take a bit longer time today. Let me explain the nonlinear regression. I'll go back to this and try to explain. Whatever I talked about using my, can you see this? Sarup?
No, sir.
Whatever. How about now? Can you?
No, not yet.
Now?
No.
What happened, man?
It is present. It is present.
দাঁড়াও আমি খুলি আগে এটা তো আমি তো অতটা ফ্যামিলিয়ার নই okay actually is you can find a line, right, that would be able to represent that one. But before I go for nonlinear regression, let me show you one thing, that if you have some data set in terms of here, right, but we can always transfer those data set in another space where it becomes linearly separable. Just I'm showing you for the separability and then go for the nonlinear regression. Here, this particular data set, you see here there are two set of data, right? Here it is blue and this red data points, and obviously you cannot draw a line to separate this data set. What you can do here, you can draw something like a circle like this, and that would, within the circle the points are blue, outside the circle they are red. Now I am giving one mapping, just simple mapping. You calculate x1 square and x2 square, and you consider x1 square as z1, maybe this one is z1 and this is z2. That is z2 is nothing but x2 square. And so you can take this point, you take, it has got two components, right, x1, x2, you square them and you plot here and put them as blue, and all these blue points, right, if this is 0, 0, right, so this point will be like this, and this, all these red points will be somewhere here. Now you see it becomes linearly separable. What we are trying to say, if you have a set of points here which are not linearly separable, it is always possible to map these points somehow in a new space where it becomes linearly separable. Okay, you draw a line there. So we will be using this particular concept later when we will study say nonlinear SVM and all those stuff. But here also what I trying to say, that if you have a data set, this is actually the input space we call, we can always calculate something new features. We can refer these as a features. Okay, we are taking that in a different dimension where something that if we could plot them, it is linearly, it becomes linearly separable. Now you work here, the same thing can be represented here as well. And this one is very famous. There is one Kovar's theorem. I'll talk about that later, and then you will be able to understand that. But what I'm trying to give you some feeling, though the data is not linearly separable, but it is possible to somehow change those data points. You calculate something new, those are called feature. These are the input, these are the features. It is not necessarily that you have to have two only. You can calculate more features here like x1, x2, or maybe simply you can keep x1, or maybe x1 to the power 3 by 2, x2 to the power 1 by 2. So something like that. You can always calculate anything, right, using these x1, x2, and they will be the new features. And you can use them, right, to represent the data so that it is convenient for you to classify them or use them. So this is one mapping is possible, that is called Kovar's theorem. I'll talk about that later again. Okay, and here I have got only one thing. Now here what I'm trying to say, suppose you have got a data set only using two parameters x1, x2, and they are not linearly. That means if you try to fit a line, linear function, a line, right, w0 plus w1 x1 plus w2 x2, you are not getting a very good result. Now what you can see that there is a nonlinear, right, you have to do the nonlinear regression. And in the nonlinear regression, what type of function you want to use, you have to tell. That is the only actually drawbacks of regression technique, right? You have to decide what the function would be. And you consider that, okay, this is a quadratic function of x1, x2. And what is the quadratic function of x1, x2? All of us know that, right? That is w0 plus w1 x1 plus w2 x2 plus w3 x1 square plus w4 x2 square plus w5 x1 x2, right? It's like quadratic function of xy. What we know that ax square plus by square plus g or 2h xy, right? 2gx plus 2fy plus c equal to 0. We know that, right? So here in terms of w, we can write it. So there will be total 6 terms in the quadratic function. Now, if I write that x1 square as maybe z1, okay? Just hold on 1 second. Let me see if I get one presentation I had somehow. This is not here, right? Is there or not? Yes, here I got, okay? Just see my note here. Now, suppose y is quadratic of x, one function only. So w0 plus w1.
Your screen is not refreshed. I think you have switched to some other one.
Oh, yes, so yes. Just 1 second. Sorry about this. Okay, can you see now?
Yeah, it's coming.
Okay, so suppose we are considering that it maybe single variable linear function does not work, and you feel that maybe a quadratic function will give us a better result. Okay, and that what will be the quadratic function of single variable? That is w0 plus w1x plus w2x square, right? This is the quadratic function of single variable. Now you can always consider this x as a z1 and x square as z2. So this is a linear function in z1, z2, right? And this z1, this is a linear, and we know how to handle the several variable or multiple variable linear function. Just now we have learned. What is z1? z1 is nothing but x, and z2 is nothing but x square. So quadratic function of single variable is nothing but a linear function of two variables, right? So here this z, a new space. Earlier we had single variable x. Now we have moved to the two variable, right, space z. So quadratic function can be expressed, quadratic function of single variable can be expressed as a linear function of two variables. Okay. Similarly, suppose we consider a y as a d-degree polynomial. So d-degree polynomial means you will have w0 plus w1x plus w2x square up to wdx to the power d. Okay, so you can consider further x or maybe say capital very high dimension. You just write down that. Now, what is x? X value you know. X is nothing but z1, x square is z2, x to the power d is z. So you can always see that this is a function of z1, z2, zd, or this is a linear function, right? But all these x for x square, x to the power d, we can always calculate. So it was a d-degree polynomial function we wanted to have, right? Which is nothing but a linear function of d variables. And linear function of does not matter how many variables, the technique we have learned, and we can do that. So any nonlinear function can be considered as a linear function, right, of a separate space. Now let us assume the function, right, it is not a simple quadratic or maybe a d-degree polynomial function, it is a combination of something like this. Now you see, this is a x, this is x squared, this is x to the power something, e to the power 1 by x, sine of 3 to the power x. X is z1, x squared is z2, x to the power 3 by 2, you can always calculate z3, e to the power 1 by x, or 4x, right? It is z4, sine of 3 to the power x, that is z5. You can always calculate. Now this is nothing but a linear function of 5 variables. So always we can consider the nonlinear function of any variables into linear function of several variables, right? So that's what is convenient for us, and we can always go for any function, does not matter whether it is linear or nonlinear, we can always consider the nonlinear function as a linear function and work on it. Okay, so I'm stopped. This one is okay. Now I'll stop it. Again, then I'll go back to my actual presentation and to this one. So I guess that it is now clear for you the regression. Regression is very easy. Don't worry about that. If you can learn for the single variable linear function, then we can extend it to multiple variable linear function, and then for the any nonlinear function as well. Okay. Now there is one logistic regression. Okay, I'll take another 5-10 minutes maybe.
I have one doubt.
Yes.
I mean, in nonlinear, what actually I could understand, like the problem is to move from the nonlinear to the linear space, so that any linear boundary can be used to separate the data.
Yeah.
Am I right?
That is for the classification.
Right. So now that mapping, whether is there any chance of loss of information? So because we are moving from one to the other mapping side, so there may be chances of misrepresentation of the data.
Yes, you are very true. In fact, you will, frankly speaking, if you just create new features or more number of features, you will not lose any information. But you may not be able to reach to a space where it becomes linearly separable. That is true. But unfortunately, Kovar, who has given this theorem, he has a very famous theorem. I'm just stating that theorem. What the theorem says is that it is always possible. Remember, it is always possible. Can you hear me?
Yeah, I can hear you.
It is always possible to transfer the points from data of a particular dimension to a higher dimensional space, where it becomes linearly separable. It is always possible to take the points from a particular dimension to a higher dimensional space where it becomes linearly separable. Okay, this is the theorem. It is possible what he says. And I have shown one example, and I can show several other examples also. There is Zor function, right? Zor point.
Yeah.
But Kovar has not given any algorithm to find out how to take those, or in which space you can take the points where it will become linearly separable. That theorem does not exist so far. It is possible, he says, but how it is possible, where you can take it in 2 or 3 or 4 infinite dimension, that he didn't say, and nobody could able to come up with any theorem or any concrete algorithm that would help us to convert or take the points to that dimensional space where it becomes linearly separable. Okay? So that's why we have to do something, some experiment or some, what shall I say, experimental stuff. And
so that means that can be treated as one optimization problem, or a kind of learning can be applied over there.
Actually, people have tried to handle that in a different way. When we study the kernel trick in SVM, we learn that. Yeah, kernel trick actually somehow, though it is not sure, but we can make sure that it is sure that we will be able to take the points in higher dimensional. Actually, in kernel, we will take the points in infinite dimension where it is always linearly separable.
Okay, fine.
Okay, so Kovar unfortunately could not able to prove it, and later also nobody so far has given any theorem or algorithm actually that in which dimension or how. Experimentally, or like whatever example I have shown you, there is a Zor points. Right? You give the points in like the Zor, right? 0, 0, 1, 0, 1, 1, 0, 1, 1. I can take those 2-dimensional point in 3 dimension where it becomes linearly separable. So, but unfortunately, there is no generalized proof theorem. Okay, now come back to this logistic regression. This is a fantastic. There is some fantastic concept of training where we do not like to predict in black and white. Maybe say whether there is going to be any flood in the coming year or not, right? Or actually, I was working on a landslide project in say hilly region, right? Most of you are staying in the hilly region, and you always suffer from these landslide problems. So if you can predict whether there will be a landslide in a particular area or not, right? If you want to predict that, see, what data you can have is that in this place there was a landslide, say last 10 years back, maybe 1 year back, or you can get a data. But what you will like to predict is that there may be a chance of landslide in this particular area. You do not like to predict there will be a landslide, or nobody could predict, right? There will be a landslide this year in this particular location, but there will be flood this one. Okay, these are rare events. So these are the stuff, or maybe that, okay, this person is going to vote or not. Here it is coming. So this person maybe didn't vote or do not like to vote, or he will see or she will surely vote, right? Instead of predicting that, what we will say that, okay, this with high probability that there will be a landslide here with probability 0.8, but there will not be a landslide here with probability 0.6. So this type of prediction we will prefer, isn't it? So whenever we do not like to predict, right, in 0-1 term or black and white, where we would like to put some probabilities, like whether there is a chance of heart attack, right, of a particular person. Looking at the parameters, you try to predict, right, there will be a heart attack or not of a particular person. And nobody likes to predict there will be surely a heart attack or not sure. Instead, we would like to add some chance or probability. In those cases, we use logistic regression. Okay. Now, if you see that in the linear classification, so far whatever we have seen, that in the PLA, perceptron learning algorithm, what we have seen is that Hx equal to sine of W transpose X. Hey, can you please hold on a second? Because here this room lab has become very cold. I'll ask these guys to increase the temperature. তো টেম্পারেচারটা বাড়িয়ে দাও, ঠান্ডা লাগছে, এত ঠান্ডা করে দিয়েছো আজকে। Because it was not working yesterday, somehow we reduced the temperature too much.
It's compensating. There also is compensating.
Sorry?
Yesterday it was not working, so today is giving more to compensate yesterday's.
হ্যাঁ, অফ করে দাও, অফ করে দাও, দরকার নেই। Okay. See, I switched it off. Okay, so in the PLA, perceptron learning algorithm, what we have done, we have calculated W transpose X, that is the weighted sum, right? Yesterday we have discussed, and we have found out W using the PLA, perceptron learning algorithm. And if it is greater than 0, we say that that particular object is in plus sign, or it is negative, we have got this one, right? This is a linear classification. And just now we have learned linear regression, and that is same as for nonlinear regression. Hs equal to simple W transpose X, right? There is a hypothesis. Value is W transpose X. Now in the logistic regression, what we want, we do not see, it is also a regression. W transpose X would have been okay, but W transpose X can be anything, right? In a particular range, 0 to 1 or something like that, and you predict. Instead, what we want is the W theta of W transpose X. We are adding one function. What this theta is, this will give us some probability value of this one. Okay, then you may say, right, why this W transpose X, this is a real number, right? Anything real, and we can always convert that to 0 and 1. Why don't we do that? You see that when we got the data, the Y values also was real. The rainfall, right, there were different value, or the credit limit, there are different values. But here, what data we have got? We have got 0 or 1. There was no landslide, or there was a landslide. The data we had is either in 0-1 term, right? The Y value was in 0-1 term, but we have to predict the a value which is in between 0 to 1. So we will be using some function that would transfer this value into the range 0-1. That's why we have written here theta. And we know, right, sigmoid function is very popular one, and we'll be using the same thing. Okay. So In the linear regression, it is sign. If it is greater than 0, it is positive. It is less than 0, negative. We are familiar with, in the linear regression term, whatever W transpose X value we got, that is the value we have predicted. Rainfall, right? We have seen that. And here, the actual value we got in terms of 0 or 1 and 1, but we have to predict something which is probabilistic in between 0 to 1. In the logistic regression hypothesis is some theta of W transpose X. All are in W transpose X. Don't worry about that. Now, what this theta value can be and what you anticipated is correct. All of you, whoever has worked in the artificial neural network, you people are familiar with this, right? Sigmoid function. So, and in other machine learning techniques, and this function of this, right? If this is S, this is theta S is equal to e to the power S by 1 plus S. This can be written as 1 by 1 plus e to the power minus S as well, right? And we have seen that. And if you see this at S equal to minus infinity, in minus infinity it is 0. E to the power minus infinity, it is 0, and this is 1 plus 0, so it is 0 by 1, so it is 0. And it is at infinity, this is e to the power infinity by 1 plus e to the power infinity, right? So infinity, infinity. Anyway, you can divide numerator and denominator with e to the power S first and take the limit, and it will be 1. Okay, so at minus infinity it is 0, at plus infinity it is 1, and in between it would be 0 to 1 value. And this function is very popular to all of us. This is a sigmoidal function, we know. So this is the function we will be using, and here. Okay, so moreover, this hypothesis Hx will be theta is represented as a probability. Okay, the prediction of heart attack. Now, what we can think of is W transpose X is a risk score, maybe X, right? You calculate the different parameters. Normally, we go for say lipid profile and all. Normally, I go for checkup every year once, right? So you check your what they are, blood pressure, sugar, and then there are several other parameters. Lipid profile, anyway, triglyceride, this, that, right? So LDL, VLDL, and all those things we calculate, we check, right? Now you take all those things and give the weightage to that, and you calculate a risk score. That is S, right? So S is the W transpose X. Now, if put that S on that sigmoid function, if it is close to 1, there is a chance of heart attack. If it is close to 0, there is no chance of heart attack. But there may be value 0.5 as well, as I said, right? It is nobody would like to predict whether there will be a heart attack or there won't be a heart attack. Instead, we try to predict that there is a chance of heart attack, right? And chance is terms of probability. That's what we will do. Now, you see that. What the data we have got the data +1 and -1. Okay. Now, for the value X, what we can say that there is a probability we can calculate like this, that XY data we have, Y is +1 or -1, right? There was a heart attack, there was not a heart attack. There was a landslide, there was not a landslide. And X has those parameter values. Now, what we can see in terms of conditional probability, that this is a binary Y, right? P of Y given X equal to Fx, a function, right? That is theta of W transpose X, Fx for Y equal to +1. Now, if this is the case, then when Y equal to -1, we should have 1 minus Fx. This is the normal rule for probability, right? So if this is Fx plus, and then for the minus, it has to be 1 minus. If this is the chance of heart attack, this is a chance of not having a heart attack. If Fx is the probability of having a landslide, then 1 minus Fx is the probability has to be of not in. There is not going to be a landslide, right? So this has to satisfy, and that particular function satisfies. Anyway, the target here is F RD to 0 This is the X, right? X belongs to D-dimensional real space, and we want to predict not 0, 1, but within the closed interval 0, 1, any value, anything between 0 to 1. So we have to learn this dx, which is nothing but S, theta of W transpose X, which will be close to the target function fx. Fx is this, right? This one. So theta of W transpose x. Remember that one. So for each xy, y is generated by probability fx. Error measure is based on likelihood. This is another one. Likelihood, instead of calculating the square error here, the probability it is always with the likelihood. That is the chance of occurring something. Now, if h equal to f, how likely to get y from x, right? So this is the hypothesis h, that x has occurred. We have seen these parameter values. What is the chance of occurring the landslide? That is hx. And if this is -1, then it has to be 1 minus hx. And fortunately, for the function, whatever we have considered that e to the power s by 1 plus e to the power s, if you just put theta equal to minus s, it is nothing but 1 minus theta of s. Okay, that means 1 minus hx is equal to h of minus x. That is the only thing, good thing here for this function. Therefore, p of y given x is equal to theta of y w transpose x. Because you see that what I said, that theta of minus s, that e to the power s by 1 plus e to the power s, right? There you just put e to the power s, you replace s by minus s, you will get e to the power minus s by 1 minus 1 plus e to the power minus s, that is nothing but 1 minus theta s, that is e to the power s by 1 plus e to the power s. You just do that experiment, you can see this one. Now see, this is what we have assumed, right? P of y given x equal to hx. It has to be there because our value we have is y, but we are assuming this as a function. So what about this? Y equal to -1 has to be 1 minus hx. That is the probabilistic term, right? Now you see, when we assume that hx is equal to w transpose x, and what is the theta function is this, and here, if your p of y given x is equal to theta of w transpose x, right, when y equal to +1, and you put multiply here with y. If y equal to +1, theta of w transpose x, no problem, that is not a hx. Now, when y equal to -1, your function becomes 1 minus hx, which is nothing but h of minus x. And here you multiply theta of minus w transpose x, and theta of minus w transpose x means 1 minus theta of w transpose x. So here, this is the generalization. Does not matter what this y is, you multiply this y here and you will get it. Actually, this particular application we will see in the SVM as well, and I will explain that in detail. So does not matter what the value of y is, we can represent that as theta of w transpose x, calculate and multiply by y. And this here, this helps us. This generalization is possible because of the function, sigmoid function we have assumed here. Okay. Anyway, so what is the likelihood measure? For x1, y1, it is theta of y1 w transpose xn, or x1, right? And likewise for all you calculate, and likelihood measure is the product of them. Okay. That means chance of occurring or satisfying this, you calculate, satisfying this, you calculate, and what is the total? So you see that product of that. That is the likelihood, okay, and product. Now to take this one, you just take, this is a product, right? So you take the log of both sides, then it becomes a summation. Okay, we have taken the summation, and moreover here, this is a maximization. We always try to maximize this probability, right? Now, if I just multiply this whole thing, both sides with a -1, then it will become the minimization of this, right? So that's what is being done here. Maximization of this particular thing is same as minimization of negative of this one. Okay, negative of this one we have done, and there is some constant multiplication here, and log function is a very increasing function. Okay, so we can monotony increasing function, so we can take the log also, and that will help us to give us such a nice summation form like earlier case. Earlier it was a summation of square terms, here summation of log terms. Okay, and this negative I can take inside and it will become 1 by this one, right? So this is again one summation form, and we like to minimize this. Actually, this one comes from the maximization of the likelihood. Okay, and fortunately, this is a very known function to us. Okay, cross entropy function, which we use in several deep learning algorithms. Okay, so likelihood measure is nothing but you just minimize this one, and this is cross entropy error. Very famous one, cross entropy, and it has a very nice properties as well. This is a convex function, so unlike the square error, it has got only one minima or one maxima. Okay, so that's why we prefer cross entropy error, and that's why there is no chance of getting stuck at local minima. So likelihood measure, and now we will try to minimize this to find a W. Okay, and there is a technique, gradient descent technique. We'll study in detail in the numerical methods, in artificial neural network, that is this one, right? I'll explain that tomorrow. So gradient descent, you just take it from me, you assume some random value in the beginning, W0, then you can find an prefer or better W1 by using this one, W0 minus eta, gradient of E in, that error, whatever we have seen. And from there, we can always calculate gradient of E in as this, and we can come up with this algorithm. So you initialize the weight W0, then you just go for a loop, calculate delta En, and then you find a modified W, right? After some step, you stop, drop, and find out the W. Once you get the W, so you get that function, right? Theta s, then you calculate W transpose X, then you use that e to the power s by 1 plus e to the power s as its probability. Okay, so that is the logistic regression. Just to summarize whatever we have learned so far, say take the credit analysis. You approve credit or not, there is a perceptron, right? There is a classification, and we have used PLA. I didn't talk about pocket algorithm, and you forget it. At least we have learned one algorithm, PLA, perceptron. For the estimation, amount of credit limit, that is linear regression, right? That is square error, right? And pseudo inverse. We have seen that, and we have learned that one. And what is the chance that person will become a defaulter, right? You can think of a defaulter. There is a logistic regression. We have used cross entropy error as your optimization function, and gradient descent we have used. Okay, so this is the summarization of whatever we have studied so far. Okay, basic machine learning, then classification, one classification algorithm, and I am telling you again, that is the backbone, the basic thing, perceptron, line. If you can work with line, you can always work with any node line or curved line. Okay, remember that one. You work with linear regression, it is easy to work in using the nonlinear regression. And then logistic regression also we have used. And here in the perceptron algorithm, there we have checked the number of errors. Classification error means how many errors are there. There is no error, you stop it. And then in the regression, we have used square error. And in the logistic regression, we have used cross entropy error. Okay, and cross entropy error is very popular one because of its advantage, right? In the face recognition and all, in the CNN, RNN, and in GAN, okay, generative adversarial network, and several other algorithms, cross entropy is preferable because of its very nice property of convex characteristics. Okay, so this is the one. Anyway, in the earlier one also I have given this one, though there are certain things which I have not talked from him, but anyway, I like his book as well as his lectures. So let me stop here, and I'll stop sharing this, and if you have any question, please ask me. Okay.
So I have a small query. Like in logistic regression, like instead of sigmoid, can you use some membership function?
Yes, you can.
Okay.
You can.
So that is called what we call fuzzy logistic regression or something like that. Or?
Yeah, but one thing, Swaroop, what you have to do is that you have to make sure that if you can do that fx, right, when y equal to +1, and 1 minus fx when y equal to -1. Otherwise, you cannot generalize. And so mathematics, if you cannot do that, then obviously you can do it, but you have to put the mathematics, right? That formula may be different. Otherwise, yes, you can.
And
right? The mapping has to be within 0 to 1, as well as that f of minus s equal to 1 minus fs. That property, those properties has to hold.
Okay. So if it holds, then only we can apply.
Yes, obviously. This one. Otherwise, we have to check actually, or maybe we have to come up with a different mathematical approach. Only the mathematics will change. Doesn't matter, but you can do it. Yes.
And one more thing, like in multi-dimensional linear regression,
Yes.
that you have shown, that is the capital W with
Yes.
some tag and then that expression. Am I right? The W, the last expression that you have shown, not W equals 2.
Yes. X transpose X equals X transpose Y. Yes.
Is it a one of the step that if we take the multiplication of the matrix and the weight matrix, not matrix, the transpose of that matrix,
Yes.
and then we are going to get the W. But is it a
Yes.
one step? Because it's a learning, it's a continuous process. Is it if I use that equation? So is it in one step, or is it one of the iterations of that?
You see, Swarup, this regression, whatever we have done, that is not a recursive process or approximation. That is a deterministic process. So it is a one-step process. You are right. I would have mentioned that. I should have mentioned that. Thank you very much. Yeah, and note that the large LPLA, whatever we have done, and whatever I'm talking about in the logistic regression, that gradient descent, they are not deterministic method, right? Or analytical method, but the regression, whatever I talked about, they are analytical and they are calculus-based, concrete mathematics, deterministic, one-step solution. Yes, whatever you said, that is one step. Yes. That means you just write down the equation and solve it. You find out the inverse and just find out and write down that W. Yes. There is no approximation.
Yeah. Any more questions from any participant? I think you also should have some questions inside your mind.
Yeah.
So it's very important, like just because until unless you have either, it means two things: either you have understood everything, or you have, you have facing a lot of difficulty to understand.
Yeah.
So anyway, both the cases you should raise your hand, or you should come out and then you ask. Then only it will actually go inside your mind.
I fully agree to that, and I appreciate that. Moreover, if you do not ask, I do not feel motivated to talk, right? Like what Swarup was telling me, it helped me, right? To point out something more. Please.
So it's very, very important. It's very, very important.
That you may feel that some question, whatever you are thinking, that may be silly, but no question is silly. I'm telling you, no question is silly.
And also, sometimes we may have some phobia kind of thinking. If I ask, somebody may laugh at me.
Yes,
so
that's what I'm saying.
Because there is should not feel shame on saying that I don't know anything. I don't know. So there is no. I mean, you should not feel any shame on that. You should not pretend that I have understood everything. So that's why it should be, because that's why I planned to have a very close kind of an environment where there will be one teacher, no other high funda lectures, only just to learn the basics. So
exactly.
That, as I've said, so possibly you're not going to get that environment. So this is the only chance. If you in the YouTube videos, and these are one-sided. You can ask. So this is the chance that at least you come out, you may study a bit of the last night. Let us assume tonight you can study a bit, then start interacting with the expert. Then I hope you will going to get that thing. And one more thing that I can tell you, it's not Dinabandhu is not stopping up to the mathematics. He is trying to map it into the probabilistic or statistical views of that. That is his video. Doing his try to solve it using statistically. So that's why both the flavors you're going to get it in his lecture. But without understanding, if you say I have a tool, and I'll download that thing, then you're not able to play with that. Yeah.
You have to feel it. You
That's
have to
why
feel
I'll
it.
ask.
Right?
Yeah, right.
So,
So
can
I'll
I
ask-
suggest something for you in this regard?
Sorry?
Yeah, can I suggest something?
Sure.
Actually, tomorrow, let us start at 11, that's fine. And past 10 minutes, we'll be discussing about today's lecture. I'll be trying to answer your questions and your doubt.
Yeah,
Please come up with some clarification or questions, whatever you have, any doubt you have in your mind, please. Okay? So tomorrow, first, we'll start at 11 o'clock and wait for your doubt clearing session. We'll have one.
exactly.
Okay?
So instead of whatever we have studied today, let us go back and open some of the material, some books, some online.
And see my notes also. See my notes also. Try to map and think that what they are.
This is the
more
best.
than
Right. This is the best way.
yes.
You are, let me tell you, you are getting our typical traditional way of tuition. Machine, you're going to get it anyway.
Yeah.
Okay. So Dibya, I think she was supposed to ask something. But you have anything?
Yeah.
No, sir. Sir, I'll just clarify my question and I'll ask tomorrow.
Sure.
I'm still not clear about the question only right now.
Fine.
I'll look at the notes, sir, and I'll ask tomorrow, sir.
Sure. So anybody? No one. So then I think we can wind up for today. Thank you, Dinamanda.
Okay. Saying something, Bidur?
Yes, sir. Sir, actually, sir, can you hear me?
Yes, you can.
Sir, actually, I'm thinking about one of the application of machine learning, that is emotion analysis from a text. So, sir, for the logistic approach would be the good approach, sir, the probabilistic approach. Because I have some hypothesis, so I need to test this hypothesis.
Yes, you can.
Sir. So I have the logistic approach is the good approach. Logistic replacement for.
Sorry, not able to understand actually.
Sir, actually, I have application of machine learning, that is the emotion analysis from a text. So for this, I have. Sorry, sir.
Sentiment analysis.
Yes, sir. Emotion analysis. Yes, sir. From a text.
Yeah. We call it a sentiment from the text. Yes.
Yes, sir. For this, I have thinking about one of the probabilistic approach. So it comes under the logistic classification,
yes.
sir.
Yes.
So we can use this logistic approach for classification of this analysis.
Yes, you can.
Thank you, sir.
And not only logistic regression, but we can use MLP also. Tomorrow we'll talk about MLP. It is not necessarily that we have to go for logistic, but you can use MLP also to estimate that.
Okay, thank you, sir. Okay, sir.
Very good. Yes.
Sir?
Yeah, Binan, tell me. Yeah, actually, you see that in the nonlinear regression also a technique to solve nonlinear problem, right? But one thing is that in the regression, that is the normal drawback of regression, the user has to decide what the function type would be. You understand? Now you give the type of function that from the data we will be able to calculate the parameter, those coefficients. On the other hand, tomorrow and day after that, we'll learn some techniques like MLP, that artificial neural network, and SVM, where you do not need to mention the form of the function, whether it is quadratic, whether it is logarithmic, whether it is sinusoidal, or it is exponential, or it is a q degree polynomial. You do not need to say. Machine itself will be able to come up with the form of the function, what nonlinear or linear, whatever suitable function, as well as the parameter, right, the coefficients of those terms from the data itself, right? That's why they are much more improved machine learning technique compared to the regression. In the regression, you are telling the machine, you prefer this type of function. Form of the function you have to tell, right? But data will help you to find the coefficients only. But the ANN, artificial neural network, as well as SVM, we will be learning later. That would help you to not only to find the coefficients, but as well as the form of the function as well. That's why people prefer to use ANN. You understand?
Okay. Related to that, like how it is related to the curve fitting?
How it is related to curve fitting? Oh, very good question. In the curve fitting, suppose you have got, say, 3 data points. Okay. Now, if you have 3 data points and you want to fit a curve, obviously in the curve fitting you can find a curve with having, say, maybe a quadratic term only, ax square plus bx plus c. There will be only three terms, right? Because you have to have 3 equations, because in the curve fitting, whatever points you have, the curve will always pass through those 3 points. It will compulsorily, in the curve fitting, those 3 points will, that means the curve will pass through these 3 points. On the regression or in the estimation, not necessarily that the line will pass through the 3 points, given points, but it will pass through nearby points, minimizing the square error. In the curve fitting, if you are given capital N number of points, the curve has to pass through all the points. You understand? For the regression maybe. But in the estimation or whatever regression we are trying to find out, we are trying to find out a simple curve that will pass through nearby those given points, so that we can find the minimum square error, right? Square error, you understand, the perpendicular error from the distance from the curve. So in the curve fitting, the curve will pass through the points for given all the given points. But in the regression, it is not necessarily that curve has to pass through all the given points. You understand?
Yeah, got the point. Like, I mean, some way, if we can have like a kind of a curve, what I could understand, like if we have not exactly the curve fitting, but some way if we can have a curve fitting kind of algorithm where it's not touching all the points, but at least close to that, I think if we make that, the chances of overfitting will be high. Am I right?
Yes, you are right. I was about to tell that actually, that if you just try to do that curve fitting, you will be suffering from overfitting. And that is the problem of overfitting, and there is a technique to avoid that one. Okay, if we had a chance to talk on overfitting, then I could have explained that one. And actually, you can listen to Abu Mustafa's, I think, 11th lecture. I remember that is overfitting. You listen to that, you will understand.
Nice. Thank you. Somebody else was about to ask something. I have seen. I don't know. Some of you already. Somebody else who would like to ask. I have seen that someone was about to talk. They may be disconnected, or I don't know.
Yeah, maybe.
She is disconnected right now, sir.
Sorry?
Sir, she has been disconnected, sir.
I think. Always there is a chance. So tomorrow we'll take all the questions, whatever we have.
Yes.
Because Dinavanshu will give chance to ask.
Yeah. Thank you very much. I want it to be interactive.
Right.
So that I get motivated.
Okay.
Yeah. Thank you.
So let us wind up today. So tomorrow again we're going to sit at 11 o'clock sharply. Thank you, Dinavanshu, for all the participants.
Okay,
Thank you so much, sir.
Thank you, sir.
Thank you, sir.